Welcome to a new test and teardown video. This time it's another Hewlett Packard, a Type 8170A logic pattern generator. I am a little bit curious if I'm able to get anything out of this without proper software, proper interfaces, and I don't have the pots. So this unit uses special pots, special connectors, as you can see as well. But maybe I can probe into this and figure out, just to get something out of it. It's also a little bit difficult to program this using the front panel. There's a lot of features with addresses and data, and then you can do this and that. And as far as I can see, the clock frequencies this one can do is all the way up to 2 megahertz, which is super slow today, but probably this is what they wanted in the good old days. So you select the different ranges here, and then you can variable the clock speed on that one. We got some different clock in and start and stop and stuff like that. And I think maybe this is the option where it says what kind of memory size we got. I think it's so difficult to operate this one, so they actually included a little operating instruction. Look at that. Oy, oy, oy. So this is just the most important things you can't memorize you got there. Oh yeah. So let's look at the back, and then we're gonna power it up. This is the rear, and we can see we got an option 001, whatever that is. Mains voltage is correct, good. Yes, of course we got the HPIB card reader, where we can set some addresses and some stuff here. So what the heck is that interface? Is interesting. And the RS232 is in the old 25 pin. And look at the baud rate selectors. 110 to 96. Oh, what? Today, I mean, if they can go all the way down to 96, I mean, yeah. So this is definitely from 1978 or something like that, right? We got a lot of stuff around probe and enable. They were all in off and they are all high. Logic polarity, all right. Definitely a unit with a lot of funky settings. I have been playing with this thing a little while now, and it is actually quite funny to poke around with here. This piece of lookup sheet here is really good and useful. It of course you need to read the manual first, and then this is the remember the most important kind of stuff, and then you will get into the rest. I mean, this is a very complicated unit, I must say. But what I can see here is some really cool features, like fill the memory with some pre-programmed patterns, like pseudo-random. And that was real easy to do. I just hold down data key and then press pattern identifier, blah blah blah, and that was E for pseudo random. And then it's actually going to say memory change, press 1 for yes, and blah blah blah. All this is actually, it's doing exactly this. And then what I did was just hit start, and then bada bing bada bum, we got data. Of course I don't have the correct pots to convert the signals that it's giving out here into correct TTL levels. It obviously needs a little bit of a pulse shaper circuit, But anyway, it's definitely working. This is just one of my data bits. I am in 8-bit mode. Oh, this is multiplexed. You can see that. You don't see this with your eyes, you only see this with a camera. So when I hit oh yeah, I actually wanted to show you something funny. I am now here in the fastest internal clock rate, that is 2 megahertz, and then look at the scope at the same time here. So if I go to the right, it goes slower, right? But this is clock frequency. So normally when you dial this way, you get more, faster, right? But here you get slower when you go that way. Huh, well, that's a little bit weird. And the trick out here is the purple channel. And definitely I can see data is repeating every time there's a trick, so that also seems to be working. I can't change the internal frequency, see? Oops, error, and it's not changing anything when it is in run mode. It's active, so you have to push stop, then it goes idle, and then you can change your clock, and then you hit start again, and then it goes super slow, and then you can poke around with the settings again here. So let's do the stop again. So low address, it is in decimal mode. If I want to, so this is my memory, I guess this is the address for where I have all my data stored, right? So address 32, decimal or hex, octal. So if I go to data, now I can input data at that address, right? So now it's 58 in hex. Nope. And I can't decimal. Why can't I decimal in data? I haven't figured that out, but I can octal or I can binary. Look at that. That is so cool. So you can I love that. So this is how you modify the content and save this, and then you can change the data stream that comes out of your parallel data interface. Oh, that is very complex equipment, definitely. Well, what I think we need to do is we need to open this and see what is inside. That is what you came for, right? So we are now inside this beautiful unit. I am very impressed about the build quality, but I mean, I don't know, why am I always impressed about that? It is an HP, and this is what they do. They just do it so nice and beautiful all the time. Ha! So we got two motherboards or back panels, back plane, and one goes to all the inputs here, and the other one goes to all that kind of stuff here. And then there is a really nice flat cable that's to all the pots, and that goes down here and here and here and here. Wow. Oi, 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 oi. Did you see that? Nickel cadmium inside. And we didn't see a sticker on the outside about this nickel cadmium. That is something you should expect to start vomit all sorts of nasty acids all over the place and completely destroy this area. So that is going to be a potential problem to kill this whole unit. So I need to take out all the boards and double check this is good and safe. I also see a little bit of that. It's not what I wanted to see in this area. Oh, we got some really nice memory chips. A whole board full of memory chips. How lovely is that? Oh, by the way, this heatsink is very, very hot. And of course it's directly behind the fan. So that is definitely the power supply. Or the rectifier, right? Yeah, that is the rectifier down there. Let's flip it over and look at this from the bottom side. So this is the bottom side, the back plane. And that was indeed a rectifier. It cannot be anything else, right? And they secured this connector. That will be all the connections for the main transformer. Also some more power supply and stuff. But we also got power over here. Okay, so this is the power, the IP address, RAM microprocessor. I can't wait to see what kind of microprocessor there's in this one. Yeah, so I need to flip it again and let's have a look at the modules. Let's look a little bit on all the boards in this fantastic unit. As you can see here, I'm proper grounded because we cannot blow up anything. So this is the power supply. This was definitely in the good old days when size didn't matter, right? So let's just make this as big as possible. Look at the pitch of those connectors. That is fantastic. So that is the power supply. And see here, the next we got two different modules. One for the IEEE interface. I don't know about those ICs. They're probably some custom. So we got clock generators for all the different baud rates and I don't know what. They look a lot. See, they all got this 1820 and then a number like that. And if we look at the others, 1820 and then 1441. See it again. Yeah, I don't know. Looks like they're impossible to look up, by the way. So let's take the next one. All sorts of nice logic. This is just a 2-layer board. It is a very good idea to have all the horizontal and all the vertical on each side when you're doing 2-layer boards like this. And then I think the next one is yellow. I really like the color coding here. Isn't that just lovely? Again, tons of logic. And that'll be all the, yes, exactly, pot driving logic. Just a 2-layer board. And that there will be the orange one, the next one. And I believe now we're starting with RAM. So 4 kilobytes. And this is half of it. This is a 2-layer board. It's also only running at 2 megahertz, right? But still, don't you just love this design? And those long wires. And this was before impedance match reflections and anything like that was a problem. See, there isn't even a ground plane or a return path on any of the signals. It's just completely open like that because the speed is so slow. Oh, I love it. But here is the other part of the memory. Look at that way. They figured out if we put those RAM chips like this, the kind of offset position, then the layout is easier. So here we got a little bit more of the memory. And that is our nickel cadmium 2-cell battery. But look at that. There is a wire in the middle, and that wire is soldered to the PCB here. And as you can see, it started to leak. So it's definitely time to replace the battery or figure out what we can do here. Maybe we can use a supercapacitor instead. So it's going to solve this. I actually want to remove this and measure the current consumption when it is in backup mode. But it will be that every time you just power it off. And this is of course only storing your own user program, so it's not a big deal if you don't have a battery really. This is the CPU card, and here, as you can see, this is a multi-layer. I haven't yet figured out how many layers, but it is at least 4 layers. Oh, I need to grab it a little bit better here. Hang on, let's put it up here so we can have a look. That one is the CPU, by the way. So we got some other support chips around the CPU, and again the manual I got and the schematics I got, it's like really not detailed enough and not in a good quality, so I can't really read what kind of CPU that really is, other than it's a Motorola. And of course the program is in EEPROMs. Got a little bit more RAM here, so that will be RAM for the program, and all the other RAM is user RAM for the data. So that is not a lot of RAM here, by the way. Let's have a look. I'll have to go and look this up and see what I can figure out. Yeah, so I'll have to go and remove that battery and clean up the table here. Look at those beautiful cables. And again, this is a single layer. See? There isn't any backplane or any grounding or anything like that. Can you imagine this today? Ooh, this would have been an 8-layer with impedance matching and all sorts of drivers in each end and all sorts of sexy stuff, but nope, not needed in 1978. Flex PCB, huh? That is some. That would have been expensive. So this is a 2.54 pitch, and yeah, it is a lot different from oh, that is some big nasty pitch. Nice. So now I took out the battery, and there's actually voltage on this battery, 2.4 volts. So we actually got the correct voltage on this battery, and it looks a little bit like this is not the original one with this tape and stuff, so that was probably replaced. And I mean, when people replaces batteries like this, why don't they write with a permanent marker on the battery the year or the date when they did this replacement? Why? So now we got no clue. Can you see what's happening here? So this is the acid that is going in and lifting up the coating on the PCB. So this is the top coating here is definitely lifted around here, and we also got some acid damages. So all this needs careful cleaning, and obviously I'm gonna add a thick layer of coating, so it's going to be ready again, and then I will have to measure the current it uses so I can calculate if we can use a supercapacitor. So that is the trick now. Oh yeah, about RAM. I promised you guys to look up this this RAM chip. So this is the NEC D5101. So this is 256 locations times 4 bits. So that means you need 2 of these chips to have a quarter of a kilobyte. Can you see that? A quarter of a kilobyte, half a kilobyte, 1 kilobyte. Oh, that is crazy. And this is of course why there's another board that's completely fully populated with those memory chips. So we got all the memory that we needed. Oh yeah. Oh yeah, about decoupling capacitors and the speed that this is running at. I mean, isn't this just amazing? We got 5 decoupling capacitors on this entire logic memory module. 1, 2, 3, 4, 5. And they're just on the 5-volt rail like that. That is just amazing. Yeah, I am a little bit impressed about how easy it was in the good old days of low speed and low rise times, because that is definitely the thing. So this is after a lot of cleaning. I think we're very lucky. The tracks are actually all tracks are gold plated. So that means when acid goes in there and lifts the coating, it's not corroding or damaging anything under there. So that's good. I was also able to clean up a lot here. On the bottom side is good. So I think I'm ready to put my own coating on top of this to prevent any further damage in the future. After all the nice and beautiful cleanup here, I soldered some wires, connected a DC supply via an amp meter. So this is 14 microamps. So this is my battery or the RAM retention power. So I would expect if I power this up, exactly it goes the other way. Now it's charging a battery, or it's trying to charge a battery. That is of course not here, right? So here we see the charge current going the other way, and it's actually trying to lift the voltage on my power supply to 3.3 volts. So this is the charge current, or the top up voltage. So now we know how this works, and we also know the charging stuff is working, and obviously there's no problem in powering this up without data retention. So I just lost my program from the last experiment, so this is what I'm going to do now. I'm going to try and set up a program and test my output, and then I'm going to look at the waveform and then power it off and try and play with the voltage and see what is my data retention voltage. I'm still playing around with all this data and stuff here, so I'm looking a little bit more on the waveforms that we see on this output that I got here. I don't even know what bit this is, but it's just one of them, right? If you look at all that, all the different levels you see here of all the idle high or whatever it is. Here my data is high and here it's low, and all these funny pulses you see here, that is definitely a crosstalk because of the single layer flat cable ideas they got, and the whole way that this is just not made to to give this or to solve this kind of data integrity problem. But it's, I think, in the pods, if you have the original pods, but as far as I just heard, they are on their way, so that is great. But I think there is some power supply here and a chip that will trigger here in the middle and then restore proper signals instead of this kind of stuff here. So then it is possible to clean this up because it's far less than the signal, right? So now what I've been doing here is I programmed it to do this pattern here, and this pattern is now stored on the scope's memory, and the unit is powered off. So now I'm going to power it on again, and then it recalls all the settings. See? All you have to do is push start, and then it's going to generate exactly the same waveform. So this proves it remembers everything. So far, so good. Well, there is not so much more fun to say about this unit. It's super straightforward. It's just dialing in your addresses and the data, and then you can go forward like this and see the content of the memory. It's actually a little bit fun to see how the user interface is done, and there's a little bit of glitches, as you can probably see in the updates of the displays. There's like tiny little graphic errors and stuff like that when it's moving fast. See? It's quite funny. So this is definitely the content of the data that you see here. But anyway, I'm going to put in some capacitors or some batteries and then call it a done deal. And there's no more to say. Thank you very much. See you tomorrow. Bye. Bye.